Hi kids, today's lesson is on scale drawings. A scale drawing is a proportional two-dimensional object that accurately represents an actual object. So a scale drawing is something like a map, or when you go into Mr. Fox's room, you have the picture of the United States there. That's a scale drawing. A scale model is a proportional three-dimensional object that accurately represents an actual object. So a scale model is something like the globe that you can hold in your hands. Or if you're looking at the structure of a cell, it's a three-dimensional diagram of a cell. Scale, then, is that ratio that compares the measurements of a drawing or model to the actual measurements of an object. So we look at it as that ratio, whoa, sorry about that, of the drawing or model distance to the actual distance. So a lot of times what I'll do is I'll just write over on the side, I'll say, all right, so it's the ratio of scale to actual. So whatever your scaled measurement is to whatever your actual measurement is. So then scale factor is a scale, so just like that up there, but without units. So a scale can be written without units when the units are the same. So in this first example, what we're looking at is, I'm doing it again to you, I'm super sorry, is what is the scale of a drawing in which a 9-foot elephant is 3 inches tall? And then what is the scale factor of that drawing? So the scale of that drawing, you take, it's always that ratio of scaled measurement, so whatever the scaled measurement is, to whatever the actual measurement is. So on the drawing, your 9-foot elephant, so that is what the elephant is in real life, appears to only be 3 inches tall. So that's the scaled measurement. Okay, so to create a scale, you're going to say, all right, well, it's 3 inches to 9 feet. That's going to reduce for every 1 inch. It is 3 feet in real life. So that's your scale. The next piece here, piece number 2, said, what is the scale factor? So a scale factor says, okay, well, I want them to be in the same unit. We're not going to convert to the larger unit. We always convert to a smaller unit. That way we're not dealing with decimals and things like that. So I know my top value is going to be, so this is going to be my scale factor. My top value is going to be 1 inch because that's a unit I'm going to convert to. So then I have to take this 3 feet and make it inches. So I know that there are 12 inches in every foot. So 3 times 12 gives me 36 inches. So then we say the scale factor of this, okay, scale factor is 1 to 36. We don't need to put the unit because they have the same exact unit. So try that, what we just talked about in number 1 with number 2. I want you to do the scale, and then I want you to do the scale factor. Pause the video, figure it out, and then unpause the video, and I'll have the answer there for you. So here are your scale. Your scale for this one is 1 centimeter is 200 meters. Your scale factor is 1 to 2,000. Please remember when you are going from this 20 meters to centimeters, you're going from meters to centimeters, so it's 2 jumps to the right. So move that decimal 2 spots to the right. That's how I got the 2,000. So on the next page then, we're going to take a look at how to use this in almost real life situations. Like if you are looking at the model of the Statue of Liberty and it has that scale, if you know what the actual length of her arm is in real life, how long should her arm in the model be? So to do this, we need to think proportionally, because if we're using ratios, the next logical step is to think about proportions, because ratios are proportional to one another. So if you have a model of the Statue of Liberty, this is its scale, 1 inch to 63 feet. The length of her right arm is actually 42 feet long. How long is the arm in the model? So if I know for every inch on the model, it's 63 feet in real life. Well, that's going to mean that, all right, well, if it's 42 feet in real life, how long should it be in the model? So we're going to create these proportions using our scales. So we have their cross products, so 63 times x, 63x, 42 times 1 gives you that 42, and then divide both sides by 63, and you'll know x is going to be 0.6 repeating inches. So you can also call that 2/3. So her arm on the model, in the model, should be 6/10 of an inch repeating, but it should be 2/3 of an inch on the actual model. So then if you're looking in reverse here on a map of Europe with a scale of 1 centimeter is 50 kilometers, London, England, and Berlin, Germany are 18.6 centimeters apart. What is their actual distance between the two cities? So here, you set up that proportion again. You have 1 centimeter for every 50 kilometers. So on your map, when you measure a centimeter on the map, it's actually 50 kilometers in real life. That's going to be the same thing, and then you have 18.6 centimeters apart. So that's how far apart they are on the map. So that's that scaled distance. So you're going to look for the actual distance, because just remember, when you deal with a scale, it is always your scaled measurement to your actual measurement. Okay, so use your cross products again. X times 1 is just x equals, and then you have 50 times 18.6, which is 930. So what's the actual distance? It's going to be 930 miles. Okay. What I want you to do now is, again, I want you to pause the video, and I want you to try number 5 and number 6. All right, when you're doing these, number 5 is pretty much the same as 3 and 4, but number 6, the power of the microscope is 300 to 1. That right there should give you a clue. You have no units. So think about what that meant. Okay, so pause the video now, and I'll fill these in. So here are the answers for 5 and 6. So in number 5, you've got 1 centimeter to 1.5 meters, so 12 centimeters to x. So x is going to equal 18 meters. That is going to be, the train is actually going to be that long. In number 6, the difference with this one is that you're given a scale factor. So it just says 300 to 1. And if you look, it says the amoeba is 0.25 millimeters. So that scale factor is actually 300 millimeters to 1 millimeter. So then you have that scaled measurement to the actual measurement. So over on the right side of your proportion, the amoeba is 0.25 millimeters long. That's how long it is actually in real life. So that is why the 0.25 is going to go in a denominator, because that's its actual measurement. So you're looking at how big will it look under the microscope. So that means how big is it going to be in your scale model. So when you do your math here, you're going to see that it's going to be actually 75 millimeters. So the takeaway from this lesson is a scale is the ratio of a scaled measurement to an actual measurement. And when you're thinking about scales and you're utilizing scales, you have to think proportionally.